Hi, my name is Roberto Amoroso, a PhD student from the University of Modena and Reggio Emilia in Italy. Today I'm going to present you our work entitled Fossil, Free Open Vocabulary Semantic Segmentation through Synthetic References Retrieval, developed together with my co-authors, Luca Barsellotti, Lorenzo Baraldi, and Rita Cucchiara. As the title suggests, in this work we tackle the task of unsupervised open vocabulary semantic segmentation, which aims at segmenting an image into regions referring to an arbitrary set of concepts described by text, without relying on dense annotations. For example, given an input image of a surfer and a set of textual categories including person, water, and sky, an open vocabulary semantic segmentation model is able to predict a segmentation mask for each of the given semantic concepts. For reference, the image shown is an actual prediction from our proposed method. Previous approaches rely on inducing pixel-level alignment in a multimodal space between textual and dense visual features, perform extensive contrastive training over vast corpora of image-caption pairs, and exploit dense annotations that are available for a limited set of categories. However, all these approaches cannot encompass the wide-ranging variability in the visual appearance of a textual category. In this work, we overcome this limitation and propose Fossil, a novel unsupervised open vocabulary semantic segmentation model that enables a self-supervised visual backbone to perform open vocabulary semantic segmentation directly on the visual modalities, leverages text condition and diffusion models to generate a large collection of visual embeddings starting from a set of captions, and retrieves at inference time the visual embeddings to obtain a support set of visual prototypes for the given textual concepts. Moreover, we also introduce OpenCut, a class-agnostic mask proposer method that exploits self-supervised dense features to partition the image into semantically coherent regions. Let's now have a closer look at the proposed approach. We start by describing the preprocessing phase where we extract a collection of synthetic references. Starting from a given caption, we generate an image through a text-to-image diffusion model. At the same time, we parse the nouns from the caption and extract their textual embeddings with a off-the-shelf text encoder like clip. The same parsed nouns are also used to extract the corresponding heatmaps over the generated image through DAM. Then we binarize the heatmaps to obtain region proposals and extract the visual features from the generated image through the visual encoder, Dino in our case. The binarized heatmaps are used to mask and pull the visual encoder features, thus obtaining a visual reference embedding for each extracted noun. We then store the pulled visual reference embeddings and the noun textual embeddings in our reference collection. Let's now move to our inference pipeline. We first extract the textual embeddings of a given set of classes. These are used to retrieve the associated visual reference embeddings, and then we apply the k-means clustering algorithm to obtain k-visual prototypes. At the same time, for a given input image, we extract its visual features through the visual encoder, and the class-agnostic mask proposal through our OpenCut algorithm. These mask proposals are used to mask and pull the visual features. Finally, we apply a cosine similarity between the pulled visual features and the visual prototypes to associate each mask with a semantic class. We compare our method in terms of mean intersection over union against recent unsupervised open vocabulary semantic segmentation approaches. Our results demonstrate that Fossil achieves new state-of-the-art performance over 4 datasets. In more detail, we measure a performance increase in terms of mean intersection over union of 2.1% on the Pascal context dataset, 5.2% on the CocoStuff dataset, 3.9% on the ADE 20K dataset, and 0.1% on the Cityscapes dataset. Here we provide a more detailed description of OpenCut, our class-agnostic mask proposer employed at inference time. OpenCut is an extension of the unsupervised instance segmentation method MaskCut. It consists of a graph-based approach that interprets the patches of Dino as nodes of a graph and the similarities among their corresponding features as edges. The mask proposals are obtained by the bipartition of the graph based on a fixed threshold. We iteratively shift the threshold to first detect and refine the foreground masks, and then detect the masks of the background. To better appreciate the contribution of OpenCut in improving the quality of the predicted segmentation, we show some qualitative examples. From left to right, we showcase the input image, the ground truth, the class-agnostic mask proposed by OpenCut, and the resulting segmentation prediction, obtained with and without employing OpenCut. Comparing the last two columns, it can be clearly observed that the mask proposals provided by OpenCut have a high degree of quality, and their adoption results in a cleaner and less noisy result. In this slide, we qualitatively illustrate some example of what is contained in our reference collection. In particular, we illustrate the caption used to condition stable diffusion in the image generation process, the resulting generated image associated with the given caption, the heatmaps corresponding to the parsed nouns extracted through done, and the binarized heatmaps, which localize the corresponding concepts in the scene and are used to perform region pooling on the dense visual features. In this slide, we provide some qualitative results of our fossil compared to TCL, another recent unsupervised open vocabulary semantic segmentation approach. In more detail, from left to right, we show the input image, its ground truth, the prediction of TCL, and the prediction of our fossil. As can be observed, fossil is capable of properly segmenting all the objects in the scene, assigning them to the correct semantic class, and providing created segmentation masks that properly align with ground truth borders. To conclude, we provide references to all the literature relevant to our method. And with these results and observations, I end my presentation by thanking you very much for your attention.